I'm going to have a little overlap with what Phil Kronberg said, just to establish the circumstance, and then I'm going to carry on with what happened in the period after that until the Radio Astronomy Observatory at Queen's ceased to exist. It began with George Harrower, who came to Queen's Physics Department from Bell Labs in 1955, and he brought an archive of ionospheric scintillation data that had been gathered at the Defense Research Board by T.R. Hartz. He personally undertook the analysis of these data, and he also had the university lease a 12-acre site in the farming area to the west of Queens for the construction of a radio observatory. There, he directed a program of ionospheric observations, ionospheric studies, and they largely were based on observing the scintillations of Cassiopeia A and other strong radio sources in the 6-meter band. This is a typical Yagi of the typical interferometer that was used for those kinds of studies. That lasted until 1962-63. In that period, his interest changed to radio astronomy, and he collaborated with Robin Chisholm of the Electrical Engineering Department, who had come to Queen's in 1956. Harrower's own research in this period became radioastronomical. He had 3 published papers concerned with the estimates of numbers of radio sources, which he used as input to the design of radio telescopes. This ties in with the log N, log S sort of controversy which was going on. And he also had a paper discussing the origin of cosmic radio sources as resulting from collisions between galaxies. You'll remember that in 1960, the energy generation mechanism for cosmic radio sources was a completely closed book. In 1959, John Hogarth came to the mathematics department at Queen's and joined the group. Previously, he had been at the Defense Research Board at Prince Albert, where he'd been involved with the construction of the big radar installation of the 1950s. He left there just before the first long baseline interferometer experiments were undertaken, and at Queen's his research was such that he became the cosmologist of the trio. And so he gave a theoretical framework to the largely instrumental work of the others. One of Harrower's papers, in fact, which deals with estimates of radio source numbers, was jointly with a graduate student named Marion Watson, whose MSc was in cosmology, and she was supervised by Hogarth. That's a little bit about the interaction amongst the members of the group. Meanwhile, in 1959, the Civil Engineering Department opened a new building, which was called Ellis Hall. And in this Ellis Hall, a professor of astronomy, who was Dr. Vibert Douglas, managed to get space for an optical telescope and also to get space for office space, to get lab space, seminar room, and stuff like that for graduate students. That was where the first half dozen radio astronomy students were trained. And if you look here, you will see some ancient but familiar faces up in the top left-hand corner. You may or may not know Sandy Sandquist, Phil Kronberg, who's the third from the left at the back. There's me. There's a guy named John McDougall, who was in the ionospheric program, and Bill McCutcheon, who hasn't changed one iota since then. Okay? And down here at the bottom corner is Professor Harrower himself. In 1960, in May of 1960, Ellis Hall became the computer center of the university. And in fact, the next year, 1961, they got an IBM 1620 computer, which Phil has already mentioned. And so we actually had the computer center of the university a floor or two below us. We really had super conditions for doing the observations, the computer observations. In February 1964, the new physics department building was opened, and we were integrated with the physics department, left Ellis Hall, and also in 1964, Harrower became Dean of the Faculty of Arts and Sciences, and he gradually withdrew from active research. Back in 1958, a year or so earlier, Harrower and Robin Chisholm had begun the studies that they intended to lead to the creation of a major Canadian radio telescope. And their ideal was a 3,000 wavelength compound interferometer. As a test bed, they chose the Mills cross configuration, which was scaled up by a factor of 10 in frequency from Mills's original. And the first cross prototype, which was actually a T, was begun in the late 1950s. There's the T there on the left, and the east-west arm, the north-south arm, and all the control buildings for it. One array was 260 dipoles. Phil has already showed a beautiful color photograph of this, but this one has Harrower in the photo. 260 dipoles above a ground plane, and you can see there were 260 dipoles in the north-south array, which is behind him. The dipoles of the north-south array were not like that, but they were actually in, or intended to be in, a 60-degree corner reflector along the north-south direction. Well, now, the east-west array would produce a fan beam, obviously, on the meridian. The north-south array was intended to produce, of course, a conical beam which could be steered, and the question was how to steer that. And by the solution that was arrived at was that the coaxial line which served all these dipoles would have an eccentric, movable center conductor. And by moving this center conductor, you could change the phase along the coaxial line, which was made of 3-inch copper plumbing pipe, okay? The main problem was, of course, the phase worked all right, but at every one of the dipole entry points, there were impedance problems. And so you had to adjust the impedances as well. And imagine doing that for 260 dipoles every time you wanted to move it. The whole thing became utterly intractable, and they, in fact, had to give that up. So, to reduce the problems, they decided, they reimagined the north-south array, not as consisting of dipoles, but as consisting of Yagi antennas. And they actually built an array, a test array of 42 Yagis, each about 10 wavelengths long. You can see the Yagis at the top there, and at the bottom you can again see, Phil has showed this already, the feed line, which was the copper pipe. And even so, the phasing problem was intractable, so they changed it to traditional sliding lines so that they could actually adjust the phase. And this actually worked. So, meanwhile, in order to make this a final system, they would have needed to build a north-south array, and they decided this was pointless, and so they gave it up. Before they gave it up, they decided that they would build yet another array, and this array consisted of 160 Yagis, which were consisting of two groups orthogonally polarized, and they were intending to measure the polarization of the cosmic radiation. It actually worked, and David Routledge, who's here, inherited the construction and actually made it function in the sense that he was able to measure the polarization of test antennas, but by this time the the possibility of building the north-south array had begun to vanish, and so they thought that they would change the idea and make this as part of an interferometer with a 60-foot dish, which was being procured at the time. So nothing seems to have come of that. Brilliant idea. The commissioning of the 60-foot paraboloid took place in 1969, and I'm going to go ahead there. I'm going to go ahead to there. There's the 60-foot paraboloid, and it was set up to be part of an interferometer with this Yagi array. And it was arranged on rails so that you could make that variable spacing, and again, nothing seems to have come of that. So that is the Yagi antenna and the array system. In the interim, George Aitken, who's very well known, was doing experiments with long baseline interferometers, and there were other things going on. I will go back one slide here. This is from the top of Bill McCutcheon's antenna. There's the Yagi array. This is part of George Aitken's experiment, and there's the ruins now of the putative Mills cross. It's no longer functional. The work at Westbrook was continued after Harrower left by Victor Hughes. Vic Hughes looked after everything from 1964 until everything was wound down around about 1970. And Hughes's idea was that, in fact, he would allow Westbrook to gradually fade away so that the students would work at other institutions. And in fact, this is a typical picture of what happened after that. There's a couple of us at ARO, and from then on, we basically did all the work that we were going to do at ARO with real instruments. I would say that Hughes transformed the focus of the group from what I call pentodes to parsecs. That means that before Hughes's day, everything was built at the university. We used whatever was available. Phil's a classic example: aluminum pipe, wire mesh, copper pipe, and pentodes for electronics. After Hughes got into this, this was all abandoned, and we went to use the facilities of others. So after that happened, we have a list of the theses that were generated. You can see the green ones were at Westbrook, and gradually we moved down into the ARO system, and the black ones are people who were doing theoretical work at all. So there is a transition right there at that particular time. So pentodes to parsecs, but it was a very active group while it lasted, and it generated a huge number of theses and a huge number of, if I may say so, first-class radio astronomers who have populated Canadian radio astronomy almost ever since. Thank you.
Questions for Dick? Yes, Phil.
Just one comment to add to what Dick said. If you look at your program and your speaker list, about half, and there's about 10 people or 12 were from Queens.
Yes.
And the list isn't all that long to start with.
Yeah, well.
Yeah.
It's undergraduate count, so. I
Yeah.
wasn't counting undergraduate.
Yeah.
You're unlucky.
Yeah, and on top of that, there were at least 11 theses in the Department of Electrical Engineering. and I don't know how many in mathematics under Hogarth. So it was really active, yeah.
Why don't you have Dave Hogg or maybe I missed it?
Oh, because I didn't know that Hogg had actually done that work. When you said he was forgotten, I was there just a couple of years after him. I had not known that. I should have that redone and put Hogg there. He was the first radio astronomer as a graduate student. By the way, I've got a kind of a fun slide here. This shows your system in 2007. Remember? Helmut has inherited Phil's system, and he went back in 2007. And here, this is the big one that got away, and that's the story.
Helmut has a title for this slide.
Yeah? Ozymandias, look on my work, ye mighty in despair.
All right.
Very good.
Questions or comments?
Well,
Yes,
I remember one day when I couldn't get to the observatory because I needed the bus to work on my array, and Helmut Hesse had taken the initiative to drive it to Toronto as his private vehicle.
Those comments actually remind me tomorrow morning during coffee break, we're going to have photos. So we'll have a big group photo. If you want, you can have, we should have a Queen's photo. Maybe you'll let Jasper in. We'll do all sorts of combinations and permutations of photographs tomorrow morning at first coffee break. Let's thank Vic again.
Thank you. Thank you.